Thank you for joining and welcome to Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. My name is Peter Hofstee. I work at IBM in Austin, Texas, and part-time at Delft Technical University in the Netherlands. After a general introduction of the benefits of shared memory acceleration, in this submodule, we'll look at CAPI, OpenCAPI, the OpenCAPI memory interface, and we'll also talk about timesis flow and MemoryInception. CAPI stands for Coherent Accelerator Processor Interface and has been introduced on IBM's power processors, but is an open standard and supported on some other devices as well, including FPGAs. The interface allows the processor to coherently share memory with the accelerator. All implementations of CAPI are coherent when accessing host memory. As it turns out, not all implementations allow for the introduction of caches on the accelerator. It uses virtual addressing, which actually in the case of power, because it has two-level address translation, it really is effective addressing, because effective addresses get translated to virtual addresses and then to real addresses on power systems. But you can think of it as virtual addresses. And by having shared virtual addressing, this allows a pointer to be passed from user space to the accelerator, and the accelerator can then dereference the pointer and access the data it points to. As I mentioned, it's an open standard, and OpenCAPI.org is where you can find the details of the standards body. A little bit of history. The idea of sharing memory coherently between a host multi-core SMP and accelerators or specialized processors goes back to the cell broadband engine that was used on the PlayStation 3. There was a prototype on Power 7, which was not called CAPI, where an FPGA was placed on the front side bus, and there was actually two FPGAs, one of which provided the address translation, and a second FPGA where the application accelerator would be placed. It became a product on Power 8, and on Power 8, the CAPI protocol was implemented on top of data packets on PCI Gen 3. And that was CAPI 1.0. On Power 9, there were two CAPI interfaces. One was to take the CAPI 1.0 from Gen 3 PCIe basis to Gen 4 PCIe, still running over data packets within the PCIe protocol. And then on a more latency and bandwidth optimized implementation on top of a physical interface called BlueLink. So this was the first implementation of OpenCAPI, but in order to kind of keep the numbering going, it was called OpenCAPI 3.0. And also on Power 10, there was a version of, or there is a version of OpenCAPI that is leveraged for memory buffers. So this is a subset of the complete OpenCAPI protocol called OpenCAPI 3.1, again, leveraged for memory buffers. This slide shows some of the many FPGA cards that support CAPI or OpenCAPI. The top two support the CAPI interface, and they look like ordinary ordinary PCIe cards, because the CAPI interface was supported in its first and second generation on top of PCIe data packets. The bottom two are cards that support the OpenCAPI interface, and you see the OpenCAPI connectors on the right-hand side of those cards. They still look like PCI Express cards. Basically, the PCI interface is used for device identification and supplying power to the cards. And by doing it this way, also a server can have regular PCI slots in which you can place also the OpenCAPI devices. On the host side, of course, there is a separate connector for the OpenCAPI interface. In the previous module, we talked about some of the performance benefits of a shared memory interface over an I/O interface. And some of that is highlighted on this slide. So on the top, you see how invoking an accelerator on an I/O device might typically happen with a device driver call, copying the data over, doing a notification of the accelerator with typically something like an MMIO operation, which in itself is an expensive kind of store. The accelerators function, and then to get the results back, an interrupt or completion of a polling, copying it back to the user space and returning from the device driver. And it's not atypical for that round trip to take something like 13 microseconds. With the OpenCAPI model, it goes a lot faster, basically because there is no copying of data or preparation needed, no pinning of memory, and the accelerator can be notified right away. The accelerator does its function, and then on the return, the completion can also be handled directly to user space through shared memory, leading to a substantial speed up over the other case. So while the software level latency reductions are most significant, also at the protocol layer, there is a substantial improvement from PCI Express and CAPI 1.0 and 2.0 to OpenCAPI. And you can see that in this slide, where OpenCAPI is able to achieve a 378 nanosecond round trip time, whereas the PCI Gen 4 requires 555 nanoseconds and even more for older generations of PCI. OpenCAPI is also quite efficient. So over a 25 gigabyte per second by 8 OpenCAPI link, similar data rates are achieved as over a 32 gigabyte per second by 8 PCI Gen 5. I mentioned OpenCAPI 3.1, which is a physical address-based interface used for memory devices with low latency, and it's a subset of the OpenCAPI interface specification. And this allows separating the memory technology, DDR4, DDR5, GDDR, non-volatile memory, from the specifics of the interface. And what you see here is an OpenCAPI memory interface based DRAM DIMM module, which is actually the memory on the Power 10 system. The high data rate, per pin, allows the Power 10 processor to support 16 DRAM memory channels compared to the typical 8 or 6 to 8 channels in other server processors. Next, let's look at timesis flow. So this use of OpenCAPI is based on the observation that with OpenCAPI, CPUs are actually routers. So if I come into an OpenCAPI interface with an effective address, the page table within the CPU through the memory management unit and translation look-aside buffers, etc., will map this to a real address. And that real address, in turn, is mapped to a particular physical location. For example, another OpenCAPI port, if that range of memory was mapped to be, on that open behind that OpenCAPI interface. I can attach an FPGA to that interface and translate the physical address range to another virtual address range that may be appropriate for another system, system B in this example. And in this case, based on the virtual address that I came in with, I might be targeting system B, C, D, E, with a load from the OpenCAPI interface, or load or store on the OpenCAPI interface on the left. In Power 10, this capability to go from a real address back to a virtual address is actually incorporated within the CPU itself, and connecting Power 10 processors to each other this way does not require an FPGA. So not only is Power 10 thus capable of being a router, it's a pretty high bandwidth router as well. You see here that there's a total of 2 terabyte per second of OpenCAPI capable interfaces on the processor. So with timesis flow or Power 10 MemoryInception, very interesting applications can be achieved. In this particular case, you see a collection of servers connected to each other that are able to borrow each other's memory. It can be used also to use large SMPs as memory servers, or interconnected large SMPs as a server with a shared address space that might range in the order of a petabyte. Finally, this activity of using a CPU as a router can be repeated. So with careful mapping of these virtual to real translations and associating physical address ranges in the different servers with the appropriate virtual addresses, a system can be created with up to 2 petabytes of addressability, limited only by the number of available address bits. So while in this course, we are going to approach accelerators mostly from a user perspective, and the enablement for OpenCAPI that I'll discuss in the next few slides is not required as prior knowledge. I think it is helpful to have a high-level idea of what is going on. So there are 3 things that you might hear. OCXL, which is the acceleration framework, and defines how you integrate an accelerator within the that leverages OpenCAPI, with the host applications. libOCXL, which is the user space access library that user code would leverage to invoke accelerated functions. And there is the OpenCAPI simulation environment, or OCSE, which is a really quite a nice environment that allows us to simulate the accelerator on an FPGA in an environment, with code running on the host as normal. So these you may hear of. You can find everything you need to create a working FPGA solution for OpenCAPI on this GitHub page. And if you're interested in interacting with the technology at this level, I would urge you to take a look. But again, doing so is not a requirement for being able to do the assignments later in the course. We will approach it more from a software perspective later on. This slide shows you that the OpenCAPI interface can be realized on an FPGA, with a moderate amount of FPGA resource. So in modern FPGAs of a decent size, there is not too much overhead for including OpenCAPI. In summary, we've discussed how OpenCAPI enables coherent shared virtual memory between accelerators and host processors with low latency and high bandwidth. We've also discussed the OpenCAPI memory interface as a standard low latency interface for memory of various types. And we've discussed timesis flow and MemoryInception, where OpenCAPI functionality is using the CPU as a router to create a shared memory, though not coherent, address space across a cluster.